Welcome students, welcome to the next session of structural analysis 2. So in the previous classes we have started our chapter moment distribution method. There we have given some steps. We should have to calculate the fixed moments, we should have to calculate the distribution factors, and then the main process of distribution will start. And we have given some methods for calculating stiffness, relative stiffness of the members. Now we are going into a numerical for analyzing the structure using moment distribution method. So we are having a proper cantilever beam. So this proper cantilever beam we should have to analyze for the given loading condition. And the same proper cantilever beam I can choose for the analysis using the basic principles of the proper cantilever beam, and also I can choose the slope deflection method also. But here in this chapter I am using moment distribution method for analyzing the same structure. Okay, so the structure is a proper cantilever beam with A and fixed, B is proper with a overall length of 6 meters, and it is being subjected to a UDL of 20 kN per meter over the entire length. And also they have given in the structure there is a point load of 200 kN at a distance of 2 meters from the proper end, or you can observe it as 4 meters from the fixed end also. So this is the overall loading structure. Now for this structure we should have to analyze. Analyze means again we should have to calculate the support moments, and then we should have to calculate the support reactions. We should have to generate bending moment diagram and the shearing force diagram. So this is the complete output we should have to generate. Now I am going into the first step. The step 1 for the distribution moment distribution method is calculation of the fixed end moments for the given beam. So whatever is the support condition, for calculating fixed end moments, what we will do? We will consider the beam as a fixed beam, right? So the given structure is considered as a fixed beam of whatever the length they have given. Yes, a beam of 6 meter length, and it is having two loads. As you already know individual formulas for two loads, I am writing 6 meter length of the beam having a UDL of 20 kN per meter intensity, and the same AB is having a point load at a distance of 4 meter from the left support and 2 meter from the right support with a load value of 200 kilonewtons. So the same supports AB, because I know the formulas for the fixed moments individually, and I am taking the load individually and using the formula for the individual and calculating the fixed moment at A due to UDL as well as this point load. Again fixed moment at B due to the UDL as well as this point load. So now coming into M bar AB, or you can as usual you can write MF AB, the fixed end moment at A towards B. Similarly the fixed end moment at B towards A. So this is the way also you can generate. Next thing, the formula. So a fixed beam with the intensity of UDL W over entire length of L. The fixed end moments will be WL square by 12 at the left, WL square by 12 at the right. So these two answers are WL square by 12 only, both sides. And a point load is being subjected eccentrically with a distance of A from the left support at a distance of B from the right support. The corresponding fixed moment formulas are W A B square by L square, W A square B by L square. So these are the formulas. You should have to remember the formulas so that only you can generate the next step. Okay. So the first formula is WL square by 12 as it is already. And also we have mentioned here I am considering the anti-clockwise movements are negatives. Only clockwise movements only positive. So for this fixed beam, when you see only this rotation, it is going in the anti-clockwise direction. That's why this formula and the value will be with negative minus WL square by 12. Here also the same thing, left side minus WAB square by L square. So minus WL square by 12 minus WAB square by L square. In this way, the W intensity we have got as 20 and the length we have got as 6 and 12. Again, this is also with the minus and this is also with minus. A 200 kilonewton load with 4 and 2 square divided by 6 square, right? So this is minus WL square 12 minus WAB square by L square. So the final answer we have got as the fixed end moment at A is minus 148.89 kilonewton meter. And then MFBA, which is plus 20 into 6 square by 12 plus, because that is also in the clockwise, 200 into 4 square into 2 divided by 6 square. So MBA or MFBA I have got this answer. MFAB I have got this answer. These are the fixed end moments at A and B, towards B and towards A. Okay. So MFAB, MFBA. Okay. These are the answers. Next thing, what we have said, we should have to calculate the distribution factors. Okay. So these two steps you can say alternatively. Someone will calculate distribution factors first and then they will go into fixed end moment calculation. Step by step they are individual. So you can go first calculation whatever you want, second calculation whatever you want. So I am going for the second step as calculation of the distribution factor for a moment table. Okay. So this moment table will generate later. Next, the step 2, that is so distribution factor step. When the distribution factor step will come? When the beam is having the number of spans like A, B, C. Like this joint conditions, whatever any type of support is there, at that time that B, the distribution factor calculation will come. Here only one beam with one support. When the joint is there, at the joint we will calculate the distribution factors at B towards A, at B towards C. Here only one beam and only one corresponding span. So there is no distribution to the other one. Anything happens at one joint, so distribution to the other ones will be calculated using distribution factor. For our problem, this step 2 is completely missing. Why the step 2 is missing? Why there is no distribution factor? Because there is no intermediate joint like continuous beam. So in case of continuous beam, calculation of distribution factor is compulsory. Here we are skipping that step because there is no continuous beam, there is no intermediate joint. If the intermediate joint is there, at that intermediate joint, I should have to calculate the corresponding distribution factors towards A, towards C. Okay. Here the step was not there. Now I am directly going into my step 3 as here I have mentioned as step 2. That is generation of the moment table. Okay. So that moment table I am directly going. Why moment distribution factor calculation? Our original step 2 in the order is not there. Distribution factor will be there only for the intermediate joints which we should have to distribute for the spans. Here only one single span, so there is no distribution to the other spans. Right? So these are entered near the ends of the span. So we have calculated our fixed end moments. If the distribution factor step is there, then we should have to develop in that way. There is no, so I am directly using the fixed end moments and I should have to enter the fixed end moments near the supports as we have shown here. See here, we are indicating the beam. No need of indicating the beam, only A and B. Okay, that also you can indicate. So simply indicating A and B with some distance. Okay, the first value is the fixed end moment at A, that is minus 148.89. Minus 148.89. And the next value is fixed end moment at B towards A, that is 237.78. 237.78. Okay. So this is step only I have done. These are the fixed end moments due to that assumption that we have taken as a fixed beam. But I should have to implement the original condition. What is the original condition? In original condition, A is fixed but B is a simply supported end, simply a prop. Okay. So for that prop, is there any movement? No, it is just having. It is not resisting. Okay. So it is simply taking. Further, there is a moment addition. Okay, that one. See that freely supported end is there at B and the bending moment at B should be equal to 0. There is no need of explaining everything because these are the first problems I am writing the steps. Okay, you can develop easily the moment table. Okay, so we should have to observe the simply supported beam is there. Whatever we do, whatever the support beams we are doing also, firstly we should have to indicate the fixed end moments and then we should have to observe very clearly about the freely supported ends. If any freely supported end, we should have to indicate. Being as a fixed end beam, it will have some moment. I have taken it because it is a fixed end moment. But originality, B is not the fixed end. That's why it should have 0 moment. But it is having plus 237.78 kilonewton meter. So that value should make as equal to 0. What we should have to do? To make as equal to 0, I should have to give minus 237.78 at the B joint. Okay, so hence to make the moment at B is equal to 0, apply a correction moment. See here, the words you should have to remember. We should have to apply a correction moment at B with which value, how much value it is already having, and that much value with opposite sign only I should have to give to make this summation as equal to 0. So initially it is having something with some sign. With opposite sign and with the same quantity, I should have to add a correction moment at the same B point. Okay. So that value I should have to indicate because why I am doing all these things? Because I have observed simply supported at the B. Okay. So once you give this value at B, you should have to remember the next thing, that is carry over moment. Yes, there is a carry over moment concept here comes. Now, when this correction moment is applied at B, half of the quantity, with which sign, how much quantity I am giving, half of that quantity I should have to write as it is at A. Because this is the span. I am giving something at B. So, half of this value should be carried over at A with the same signs. So, initially the first row is given with fixed end moments and the next, to make this freely supported ends moment as 0, I have given the negative sign of 237. As this negative 237 has given in the anti-clockwise direction at B, what happens? As I am giving an anti-clockwise moment. Initially, what it is indicating, see here, this beam is having anti-clockwise, this beam is having a clockwise moment. That is the first step of indication. Later, what I am doing, this is not there, so that I am giving an anti-clockwise moment for making these two summation is equal to 0. As I am giving this answer, there is something is happening at the A. Okay, due to the application of this support moment or addition of some moment at B, there is something happening at A, that A is having some carry over moment. That carry over moment value is equal to half of the applied moment with the same sign. Okay, with the same sign, the same value will come here. Half of the value will come here. So, half of the minus 237.7. With which sign I have given? With the same sign I should have to indicate here. Half of the value we have got as minus 118.89 kilonewton meter. That should be written at A. Okay. So, this is the process we should have to go for the next step. Now, after getting these things, after giving the simply supported ends answer, I should have to do, there is a finalization. So, we should have to sum up whatever the things are happening. Now, draw two closely spaced lines so that, and then we should have to add the results. Here you can observe a vertical value. So, summing up these two with as it is. So, plus 237.78 minus 237.78 addition will give 0. And then on the left side we are having some values. So, minus 148.89 minus 118.89 which came as a carryover moment. So, this value is, correction moment and due to this correction moment, this is half of correction moment, which is equal to carry over moment. So initially I have indicated fixed end moments. Later I have observed there is freely supported end. Further I have given correction moment. Due to that correction moment, there is carry over moment. Now I am adding those two values in the vertical. So we are getting some final moments at the support A, final moment at the support B. As we have given that, it will come 0 as it is. So this is the final support moment at A. So in this way we have calculated support moment at A towards B. Now what we should have to do, as we have already got, see here, when you indicate this as negative, so it is going in the anti-clockwise direction, which in generally we indicate it as hogging type moment. And this hogging moment, for the actual picture, using the support moments line and using free BMD, correct? So using support moments diagram and free BM diagram match, and we will get the actual bending moment diagram. Okay. So after getting the support moments answer, the next step or the next thing we should have to generate is bending moment diagram. In that bending moment diagram, there is an involvement of free bending moment diagram. Okay. And the generation of bending moment diagram after calculating the support moment at A and support moment at B. So the support moment at A is equal to, if you want you can write, okay, at A is equal to 267.78. That if you want you can indicate as it as an hogging type moment, or with the minus sign you can indicate it as a sagging type moment. And support moment at the B is equal to 0, as we already know, which is 0 only because it is simply a proper type end. Okay, these are the support moment calculation. Next we are going into generating the bending moment diagram, as in that involving support moment answers and also free bending moment diagram also. So that the BMD can be drawn by superimposing the free and fixed bending moment diagrams. Yes, this thing only we have mentioned just now. Free bending moment diagram and fixed bending moment diagram. For this BM diagram, we will generate the original or the actual bending moment diagram. Now, to draw the free bending moment diagram, let us consider the span AB as a simply supported beam carrying the given loading condition. Yes, as the given structure is a proper line structure having a UDL, having a point load, but for giving a simply supported bending moment diagram or the free bending moment diagram, I should have to consider it as a simply supported beam having as it is, whatever the load it is, with that as it is load I am considering the structure. Okay, so in this way we have got support A and support B as a simply supported beam. Why I have done? Because for getting the actual bending moment diagram, this is the step. I should have to generate individual free bending moment diagram and I should have to involve the support moment diagram. Merging or superimposing those two, you can calculate the actual bending moment diagram or you can develop the picture. Okay, so this is the structure. For this structure, for calculating, so remove all the things in your mind. Up to that part only we have taken new. The remaining things are very common for you. Only calculation of support moments. In the last class also we have discussed the same. The calculation of support moments is different from different methods. Slope deflection we will calculate using slope equations. Okay, or MA involving theta and deltas. We will calculate some MAB, MBA like those equations. And in some other case we will use some other method for calculating the support moments only. So here I am using the moment table or the distribution table for calculating the support moments. And after calculating the support moments, the remaining process is as it is. So for generating the original bending moment diagram or the actual bending moment diagram, we should have to consider whatever is the supporting condition, I should have to take as a simply supported beam. If it is a continuous beam, I should have to consider each span as a simply supported beam, and we should have to generate the free bending moment diagram for the loading sections, right? So this free beam or the simply supported beam having the original load, this you should have to generate free bending moment diagram, or this simply supported beam should get the this structure's bending moment diagram, as it is not a single load. If it is a UDL, a simply supported beam with UDL, if it is there, yes, I can write UDL structure and I can directly superimpose. Or if it is a point load at center, I can develop the free bending moment diagram and I can superimpose with the height also as it is. If it is some eccentrical loading, yes, further the structure also I can superimpose, because I know the maximum bending moment and I know the maximum bending moment answer, and also we know the free bending moment diagram shape. But here the combination of load is there. So generating the free bending moment diagram is also a big step here. Further, so in keeping all the things aside, the next thing is generating the bending moment diagram for this structure. For this structure means we should have to analyze it as a simply supported beam. Simply supported beam having some loads. For these loads, we should have to analyze it. Further, a simply supported beam's bending moment diagram will become after we will calculate the support reactions. Okay, so for the free beam, what are the support reactions? This is not the actual structure, only this is a free beam. So for the free beam, what are the support reactions? How I can calculate? Simply VA and VB answers. So these VA and VB answers we can evaluate. So VB taking moment about A. So VB into what is the distance? 6 in the anti-clockwise direction. And also we are having 200 into 4. And also we are having 20 into 6 into 3, which is equal to 0. So using this step, we have got that VB answer taking moment about A. The VB answer we have got as 193.33 kilonewtons. And then VA is equal to total load minus, which is equal to 200 into 200 plus 20 into 6, 200 plus 20 into 6, which is the total downward load, minus how much VB? 193.33. And we have got the VA answer as 126.67. So for the free beam, I have calculated the support reactions. Using the support reactions, can I calculate bending moment at different points, taking different spans like equations? Yes, but no need of taking more spans, using the support answers, and in the point C, here I can conclude, or you can generate the next step also. So for that free beam, what is the bending moment at A? Is 0. For the free beam, what is the bending moment at A? B? 0. And the next thing is bending moment at C answer. How I can calculate? Now, bending moment at the point C, that is VA into 4 and minus 20 into 4 into 2. And VA into 4, how much is VA? VA is 126.67. So, 126.67 into 4 minus 20 into 4 into 2 is the bending moment at a C point. Why I have not considered the load? Because 200 into 0 on the left or on the right. Bending moment at any point on the left or on the right is same only. So, up to this position, what are the loads involved? The corresponding moment I have given, and the value we have got as 346.67. So, connecting the 0, 0, and at a C point 346.69, you can calculate or you can generate the free bending moment diagram. Now, the next step is generating the actual bending moment diagram. The actual bending moment diagram generation will be involved by superimposing the free BMD and the corresponding BMD. Not needed by indicating fixed BMD from the support moment diagrams that came from considering the fixed beams only. Okay, so I am indicating the original structure, as I should have to indicate the original structure. So the original loading with the fixed end at one end, fixed support at one end, external loading, external point loading, and prop. And we should have to indicate the support moment. What is the support moment? At A I have got that value is 267.78 kilonewton meter, that too in the hogging condition. We have generated in the previous step itself, right? So at A, in the hogging, only in the bend moment diagram only hogging will generate above the structure and sagging also will generate above the structure. So remove those two only, you will get the original answer. So at A, what is the answer? 267.7, and that is connected to 0 with a straight line. Okay, and then the next thing is 0. At the C point, we have got a value of a bending moment as 346.69. Up to that height, we should have to generate the curve and then connecting point. Now, how this condition comes? Some 346 something is there, right? So originally support moment diagram and then this free bending moment diagram. Superimposing that, we will get the original structure. Now with respect to the support line, so this is the structure we have got. Now support moment line is the main reference for us. Below that we will indicate as some value, above that we will indicate as some value, and the corresponding heights, how much you can evaluate, that you can generate from the structure from the similar triangles. As from 0 there is some 267 like value, and at 2 what is the height. So after knowing the height from the basic simple principles and removing that height, you can generate this total height, because I know the total curve height and I know the portion height. So this height you can generate, and that answer only you should have to indicate in the bending moment diagram picture. Now you can observe the answer as 257. Okay, so this 267.78, and below the supporting moment line, that like original bending moment diagram, above the line that is positive, below the line that is negative, as it is below the line that is negative moments and above the line that is positive moments. Like that only here also you should have to indicate. Generally what we will do for the basic structure when we do like this. Okay, so above the baseline the corresponding is positive moment, below the baseline the corresponding is negative moment. Here our reference is the support moment line. So below the line that is negative, above the line that is positive, like positive y and negative y, positive y and negative y. So above the line that is positive line and below the line that is negative. Okay, and the height, how it came, using the total height of the structure, using the total height from the free bending moment diagram, and also using this height from the similar triangle conditions. Using these two answers, at this particular loading point I can calculate the value. That answer they have given as 257.408. So this is the generation of actual bending moment diagram. Up to this, the generation of bending moment diagram only over, and then we should have to generate the shear force diagram. So what the shear force diagram is involving? So in case of a shear force diagram, the thing you should have to involve generation of the actual support reactions. Yes, for calculating the shear force diagram or for generating the shear force diagram, I should have to evaluate the support reactions for the actual beam. So I am taking the actual beam as it is. Okay, actual beam only we have taken, and for that actual beam, what we should have to do? Again, support reaction calculation is involving moment equilibrium or generally, and here support reactions, how we will calculate? As you already know the support moments, making the support moment at any point is equal to bending moment at that point, I can calculate the support reaction. So actual support reactions condition. So what is this actual support reactions condition? The remaining steps are repeatedly. How many methods you learn also, these methods are same. Okay, support reaction calculation. Once calculating the support moment, making that the support moment is equal to bending moment at the support. So that is answering will give the support reaction of that particular position. Okay, now first I am calculating bending moment at A for the loading. Okay, so bending moment at A for the given structure. So it is causing a sagging type. So VB into 6, and it is having minus 200 into 4, and it is having minus 20 into 6 into 3. Right? And involving all these things, we can generate this answer in this way. Sagging way is equal to, as I have considered saggings as positive, right? So sagging is positive, hogging is negative. So I am indicating this is the support moment, and this VB is the unknown here. And how I can calculate VB? Because the bending moment at A from the loading structure is equal to the actual support moment at A in the sagging condition. Because for bending moment, I will consider saggings are positives. Bending moments I consider saggings are positives. So this is sagging type moment of A. But originally I have hogging type moment answer. So for converting the hogging moment at A to sagging, I should have to indicate minus 267.78. Because at A, in hog nature I have got the answer. In hogging nature I have got 267.78. But here I should have to equate sagging natured moment. So in case of sagging natured moment, this answer is minus 267.78, and equating these two answers, you can evaluate the corresponding VB. So equating both, I can calculate VB, which is equal to 148.7 kilonewtons. And this VB, once you know this VB, you can calculate VA. How? Even though it is having moments or anything, this vertical forces involves only vertically upward and downward loads only, not even any other moments. Vertical loads only it will involve. Yes, as it is having something like this. So VB I know, this load I know, this load I know. VA, how I can evaluate this VA? So VA plus VB is equal to total download, that is 200 plus 20 into 6. So VA plus VB is equal to 200 plus 20 into 6. And the previous step only we have got VB. So VA is equal to 200 plus 120 minus 148.7. So for that we have got the answer as 171.3 kilojoules. Yes, the actual support reaction in the structure. Previously also we have calculated support reactions. How? Those are the support reactions for the simply supported beam. Here, this is not a simply supported beam. This is the original structure where it is having fixity at one side, prop at another side. So, in the original structural combination, I should have to calculate original support reactions. Which term helps us for calculating the actual support reactions? The term helping us is the bending moment at the support is equal to original support moment at the support. Okay, support moment at the point is equal to bending moment occurring at the support. Okay, so using that conditions we have calculated two answers, and then we are going into the actual shear force diagram. So for generating the actual shear force diagram, we should have to first indicate what are the VA 171.3. and VB 148.7. So this is the original loading conditions. First shear force, no need of indicating moment because the shear force also involves only vertically upward and downward loads only. Firstly, for the AC span, because it is having a load variation that I am taking with respect to spans. So, firstly, I am taking a section like this, and the corresponding spans bending moment, so shear force, you can write as from the fixed end I have taken. If you want, you can take from the right side also original shear force structure, how you develop the shear force diagram. In the same way you can develop, but only I have started from the left so that I have given, not needed to mention. Anyway, from one span you can solve, you can generate the shear force diagram for the given loading, as you already know the support reactions and the external loads. Okay, so on the left side, Fx is equal to left side upward plus Va minus 20 into x. Okay, now at the point A and at point C. So this is my C corner. At point A, which is x is equal to 0, which is how much we have got? 171.3 minus 20x, that is Fx for AC span. So which Fx is equal to 171.3 minus 20 into 0. We have got a shear force at A as 171.3 kilonewtons. And then at x is equal to 4. So 171.3 minus 20 into 4, we have got the shear force at C as the next span. I am considering the next section, which is at a distance x from A. So the corresponding Fx is equal to left side upward Va minus 20x minus left side upward. Up to that position, what are the loads involved? That only I have written. Okay, VA 171 point. How much we have given here? 171.3 minus 20x minus 200. So that is the pointer as it is after crossing C pointer. So once you substitute x is equal to 4. 171.3 minus 20 into 4 minus 200, which is equal to how much we have got in the previous step? Minus 91.3 minus 200, which is minus 291.3. Sorry, this one is plus 91.3, this one, and this is minus 108.7 kilonewtons. Okay, so that value minus 200, and then substituting it is equal to x is equal to 6. 171.3 minus 20 into 6 minus 200, you can calculate 48.6. As that is the support reaction at B, right? Shear force at B is equal to support reaction at B. And then generating the original shear force diagram. So we have calculated shear force at A, shear force at B, so at C in AC span, and then we have generated shear force at C and B, so in this CB span, and overall indicating positives and negatives above the baseline, positive, below the baseline, that is negative. So 171 up to 91.3, that is positive. Again from 0 to 108, from 108 to it has dropped to 148. So 171.3, 91.3, 0.3, and here from the below the baseline 108.7, and another condition 148.7. And connecting line is, you can observe there is a single degree straight line connectivity because there is single degree power. So connectivity is a single degree straight line answer. When you see the structure, it may appear like this: 171.3, 91.3 in the positive, below the baseline 108.7, and that has continued to 148.7. So this is above the baseline positive, below the baseline negative. This is the actual shear force diagram. When you indicate all the things at a time, it may appear like the whole structure. So the given structure with the loading and the actual support moment answer I have got. If needed, you can indicate that. So the actual support moment I have got as a hogging type of 267.78 kilonewton meter, and a vertical support reaction VA as 171.3 for the actual structure, VB as 148.7 as the actual structure, and then superimposing the free BMD with the support moment bending moment diagram, we have got the actual bending moment diagram, and then from the corresponding points you can indicate the shear force diagram. Shear force at A support, that is equal to the vertical support reaction. Shear force at C point is equal to the corresponding answer, and then shear force at B is equal to the support moment at the support reaction at B. In this way, we will analyze a complete propped cantilever beam using our method of distribution or the moment distribution method. So in the next class, we will go into a continuous beam for analyzing. It is involving both you given loading conditions as well as. So simply, when you see a simple propped cantilever beam, it is involving all these things, and it is having UDLs and it is having some pointers, and this analysis we have done, and in the next you can have some continuity with some supporting conditions. Okay. Thank you for today's session. We will join in the next class.